That's why when we tried to scale the devices, we had to be very aware of it and control that tail in process design, which ends up to be ultimately, he likes the word, thermal budget. Okay. So, it's very important to recognize how the interplay of all kinds of things takes place in generating the right integration and right device design. So for ULSI, we use ion implantation, and that is one much easier way to control thermal voltage. Okay. And especially when you use lower energy implanter. Lower energy implanter is very tricky in design. That's why, it took a long time for the industry to develop lower energy implanters. And much strides were made to enable this sub-100 nanometer technology, because they heavily depended on those kind of implanted designs. Diffusion system, all diffusion systems were open tube. Sometimes it's still used now. LSI time frame, as I said, 70 to 90. The old system was you use some sort of infinite dopant source at the surface, protected by an oxide nitride layer and elsewhere, because that's where you don't want the dopant to move in. And then you do drive in to get a certain profile and purity concentration. That has been much changed. For ULSI, doping using ion implantation is employed to control thermal voltage. So, we used all kinds of source of dopant. In the past, we used to use glass, BSG or PSG, in the very early days. That was done away with later by direct solid source, like for phosphorus, is still used in the implanter. Liquid source or gas source, depending on their availability and usability, and the so-called furnace designs and controllability. Solve the problem, which used to be not a problem of heavy metal contamination back in the old days, is no longer a major problem there. So, that's more history. So, as I said, those guys will help you to get some framework of modeling of diffusions, and provided quite a bunch of information that Sanjay has readily provided me to help you learn about modeling. So I think they will use some of his approach to modeling. All right. What you see here. Now, of course, I got this place. When I try to make a table, it never comes the way I want. That's as much as my learning of word processing is. So pardon me for that. That too I learned in a lot of duress, because when I started writing my book, I said, oh my goodness, who is going to type it for me? Who is going to do the table? Who is going to do the artwork? They don't exist anymore in my world. So I had to learn in a difficult way, bits and pieces, and not very good at it. But eventually some folks came along and helped me out. So I was able to write the book. It's a long story. But so unfortunately, I had another column here somewhere And then I see they have gone inside here in my way of making tables. These are the machines we used, Extrion, Nova, two broadly defined implanters we use. There may be more nowadays, I haven't kept track of them, but those are the ones where we could implant a whole range of impurities with a whole range of energy levels. And those were used not only for us to develop the technology, but also used for developing manufacturing capabilities. So, for everything that I'll talk about with you tomorrow, assume we're using implant. We're no longer using, because gone at that era, the old way of doing diffusion. It's all implanted diffusion. And I will touch upon when you implant, especially when you implant with higher energy, we create a lot of damage, crystal damage. So we got to take care of that damage. So we need some appropriate thermal imaging so the atoms can run around all those gobbledygook that we created by implanting with so much energy, because we created a lot of defects by forcing these implanted atoms inside the body of silicon. We've got to get rid of them, otherwise we don't get good mobility, we don't get good device characteristics, all that kind of stuff. Then the question of thermal budget comes in. Because we are limited in thermal budget, which is very precious, we have to allocate them very precisely. So we want to clean up the mess we created by putting the impurities in silicon, but we want to do that with least amount of thermal energy. And that happens to be the name of the game in integrating technology. How we integrate the technology so that we could recover those damages, but put the least amount of thermal budget into the entire way of doing the integration. And that has been one of the major of technology integration when you scale the technology. We succeeded, not to the ideal way we want. There's nothing ideal in this world. But we learned a lot. And now some of the tricks we played off of is that we will hold off that particular thermal treatment towards as late as possible so that we use the total amount of thermal energy to the least extent. So we had to carefully assess how much temperature we are putting in where and why. The problem comes in is that when you do a certain implant, you create damages. You have to activate the impurities. The impurities are not activated at that point. So how do you know what you have done? So what we used to do at every step on the way, we'll take some wafers, push through the entire thermal budgets, and then make all the measurements, at the end measurements. These are way of evaluating whether we're doing the right track or in the right track or not. It's a very cumbersome, there's no better way. Because we wanted to reduce thermal budget as much as we can until we attain our goal. Because if you don't, we run into more fundamental problems. Right? For channel effects. No good. People, no good. So, if you look at these numbers, and I encourage you to entertain them. You will see that there's a whole bunch of, can you lift it up a little bit? See, to integrate that technology back in 1987, 88, 86, or maybe even earlier, actually in 86, we were manufacturing the high body, this, where the world has no knowledge how to do this. But back in early 80s, actually, when we were putting these things together, we're talking about 11 kinds, okay, at different stages. They're progressively, as you integrate, 11 diffusions. 11 implants, 11 diffusions. Take a good close look at those. I leave it with you to go to figure out why we did this in that order. Okay? Here's something I will tell you eventually. But recognize that they are done in certain order, which is very important. Recognize also there is a wide range of dosages. Wide range of dosages. So that tells you which one is lighter dose, which one is heavier dose. Which one is deeper by the energy, which one is shallower. Okay? So there's a whole bunch of diffusions that's needed in CMOS technology. Remember that CMOS we showed you, isolation, peak fed, and that. So you have a whole range of, to build those, you need level diffusions. And they have to be in a certain order. And they have wide differences in terms of energy level and dosage level. So go take a look at degrees. You know, sometimes when I put it 0 degrees, that means normal incidence. There are other tricks we play with angular incidence to make the device work, lateral profile work better. That's not in here. But never mind. The point is that there's a lot of information here. And if you have a bunch of questions based on that information, by all means, get in touch. So that's the part of where we learn the details. So, just to give you the flavor that ion implanting is the method of diffusion today, us as well. Gone are old days of doing diffusions and impurity. Our control is getting much more tighter because we have much more available low energy implanters, and we're doing very tight control of impurities in very localized ways, and we are annealing them out. There is one thing I forgot to mention and not put it in here. Oh, we'll talk about it. In fact, I will add to it next. We have the lecture next Tuesday, so maybe I'll add some substance to it to show you how we get rid of the damage and what are the options we got. And depending on how we take care of the damage, we have different profiles. So we have to do, we have to sort of compromise certain things. So I'll talk to you the more details, the nitty-gritties of engineering in terms of diffusion and profile engineering. But important thing is recognize that implantation is the way to go. Implantation has its own pluses and minuses, but that's the only way you can control in today's world of very highly scaled technology. And we play all kinds of tricks to recover and activate the impurities. And one of the very widely used today is called rapid thermal annealing, RTA. So we put only that much of thermal energy in a very short time to to get the work done so that the thermal budget is minimized. So the lateral movement is minimized, vertical movement is minimized, but defect is eliminated as much as possible. So with that notion of mind, I'm going to end this class for the day. But we'll pick it up briefly, some of the ion implantation induced damage and annealing tricks, and then we'll move on to depositions, different films, and then going up to the contacts and back end, and metallurgy and interconnects and all that kind of things. Finish up the elements of integration. And then we will go how to really do technology and device design in great details. Once we have this key elements, you got a grasp of it and why we do what we do kind of thing. Okay? Thank you very much. And any questions?